Hello everyone, I, Daniel Nguyen, will be going through a deep dive of antenna and packaging, which is part 14 in this packaging series, with work done under the supervision of Aslam Khan and Dr. Naveed Asadi. The content of this video will go further in depth from the content of the previous video in this packaging series. The focus will be a deep dive into antenna and packages, also known as AiP. It will be outlined by a quick overview of AiPs, design basics, history, types of traditional antennas, application and advantages of antennas and AiPs, limitations of traditional antennas, structures and materials of conventional AiPs, and the video will close off with the challenges of AiPs and the glossary for abbreviation and acronyms. Rehashing from the previous video, what makes antenna and package technology different from current and past technology is that typically antennas are discrete and separated from the transceiver, also known as the RFIC, as shown as the figure in the bottom. While with AiP technology, the antenna and RFC die are both embedded together within a single package, rather than being separate. AiP allows for a smaller size for the overall chip, which also provides shorter wiring or travel distance between the transceiver antenna for the signal, and overall simpler design. As shown as the figure on the right, the AiP module reduces the size by making the transceiver a part of the stacked layers and utilizing the same wiring as the antenna. Moving on to design and basics of antennas. Antennas themselves are fixtures that transmits or receives radio waves within an open space, and both converts the waves into electrical signals and signals back into waves. The main parts of the antenna are the patch and feed that are usually made up of conductive metals, copper shown in the figure on the right, to transmit electrical signals, and it sits on a high resistivity silicon, also known as HRSI on-chip layer. Following the top HRSI layer are the solder and silicon dioxide insulated layers with a conductive radiator, aluminum in this case, that radiates the radio waves, which ends off with another HRSI layer and copper layer that acts as a ground. In antenna and packages, the entirety of the AiP acts as the antenna, package and all. Good AiP designs incorporate both traditional antenna characteristics and specific package construction. Antennas function through their capability of transmitting and receiving signals, and that is heavily affected by the size and shape of the antenna. The size of the antenna is directly proportional with wavelength, thus being inversely proportional with frequency. The smaller the antenna, the higher the frequency can be transmitted. Other important parameters to antenna performance are radiation pattern, which determines the amount of radiated energy in space, input impedance, which maximizes transfer of power from the antenna to transmission line through matching of inputs, radiation efficiency and power gain, which shows how effective the antenna is at transmitting waves through measured loss of power against power radiated. And then lastly, bandwidth, which specifies an unvariated frequency range of the antenna with specific parameters. All these parameters work together to make sure the antenna is functioning correctly and efficiently. The figure on the right demonstrates the antennas in action, where the electrical signals from the transmitter goes through the transmission line and then is transitioned into waves by the antenna, and then vice versa, being received by the antenna and then transitioned back into electrical signals for the receiver. Antenna technology predates the 1940s. Before World War II, antennas were wire-type antennas, made up of only single elements or arrays. Once the 1940s came around, other radiators arose, mostly made up of aperture-type antennas. These antennas were optimized for wave radiation and enabled communication, radar, and remote sensing technology at a basic level to come into play. At around the 1950s, frequency-independent antennas broke through antenna evolution, increasing max bandwidth for antennas, which allowed for technology such as television and point-to-point communication. It was not until the 1970s when the next breakthrough came into place with microstrip patch antennas. These antennas were simple, lightweight, inexpensive, and low profile compared to its competitors, and became the reference for antenna and package technology, one of the references. In the new millennia to now in the future, integrated circuits and radiating elements are being combined into a single unit, becoming the now antenna and packages and antenna on chip technology. Moving on to different types of antennas, which are sorted by their application classifications. With basic antennas, they are typically sorted into wire antennas and aperture antennas. For wire antennas, the first antenna is the dipole antenna, as shown by figure number 1. The dipole antenna can be printed on a substrate typically of fused silica and is designed with metal bars for surface wave suppression. Monopole antennas are very similar, except instead of it stretching out in two ends, it is only in one single direction, as shown in figure 2. Loop antennas are also similar to dipole, but the shape is circular, as shown in figure number 3. Here, 2 bonding wires and 2 pads are connected with one another. For aperture antennas, one of the most popular aperture antennas are slot antennas, which differ from wire antennas because it's more of a metal casing with cutout slot openings throughout the casing. And the slot is fed into a ground plate on the substrate. Unlike basic type of antennas, popular antennas are usable for antenna and packages because of their form factor. They are all smaller, compact, lightweight, and low profile compared to your usual basic antennas. They also have low power handling capability in comparison. And the most common types of popular antennas are microstrip patch antennas, Yagi-Uda antennas, and grid antennas. Microstrip patch antennas has a conductive metal on a grounded substrate that is fed against the ground. Some of the disadvantages for patch antennas is that it has a narrow impedance bandwidth and is susceptible to warpage. Yagi-Uda antennas has a parallel metal line driver, reflector, and director on the substrate. The disadvantages for Yagi-Uda antennas is that there is non-polarization diversity and is sensitive to the location on the PCB. Grid antennas are denoted by their interconnected rectangular loops, and they are printed on top of the grounded substrate. The disadvantages that come with the grid antenna is that it has a narrow gain bandwidth and a pattern squint. Moving on to the applications and limitations of antennas and AiPs. Traditional antennas typically are only used below 60 gigahertz, and it's most favorably operated at 2.4 and 5 gigahertz frequency bands. The typical applications for traditional antennas are Bluetooth radios and Wi-Fi. However, a lot of limitations come up with traditional antennas, such as trying to reduce the antenna size and low loss interconnection for them. Antennas have a longer distance of connection, but typically has slower speeds. And to reach higher frequencies, it can be very expensive, bulky, and heavy. And because of this, also not integrated with solid state devices, which is why antennas are typically used at lower frequencies. However, antenna and packages can operate at much higher frequencies than antennas, and they are typically operate around 60 to 100 gigahertz. Antenna and packages are one of the main technologies to operate newly millimeter wave technology, which is from 30 to 300 gigahertz. The most favored and typical use for antenna and packages are at around 60 plus gigahertz frequency bands. And their typical applications are radios, phones such as 5G, satellites, and radars. And antenna packages, although they have faster speeds, they do typically have shorter distances for reach than regular traditional antennas. But antenna packages happen to be more low profile, smaller, lightweight, compact, and are a lot easier to fabricate and integrate with solid state devices than traditional antennas. Now, for over 100 gigahertz, antenna packages can be used, but typically once it reaches over that range, antenna on chips take over from there. For current AiP packaging technology and components, there are 3 choices for the routing layers that are used for high production: lead frame, laminate, and redistribution layer, also known as RDL. Lead frame usually uses wire bonding and is coincided with quad flat no leads, also known as QFNs. Here, there's a molding process where the die is typically encapsulated the mold compound, which provides mechanical environmental protection of the die. And this can be very robust, inexpensive, and causes the package to be flexible to thermal expansion. For laminate, this is more coinciding with flip chip bumps, as there are multiple layers of conductor and glass fiber reinforced epoxy resin as a substrate. And with the epoxy underfilling, there's better performance, and because everything is conductive layers, they allows for soldering balls to be used instead of wires, and so this causes the better performance due to shorter distance time with the signal travel. And then this is also known as flip chip, and typically seen with ball grid array. Redistribution layers are typically coincided with wafer level packaging, and they are conductor layers that are sandwiched by dielectric layers. This is done through layering and patterning, and they're then through silicon vias that are vertical electrical connections that completely pass through the silicon wafer or die. And this is where the electrical signals move through wafer level packages. For ball grid array and quad flat no lead, these are typically slightly more common than RDLs. And it's because the choice of BGA or QFN package types are typically dependent on the requirement of input output counts by the die, and because ball grid array packages usually has higher input output counts with the same body size, BGAs are more common. The figure shows QFNs and BGAs respectively. Moving on with the materials and processes of conventional current antenna in packages are low temperature co-fired ceramics, also known as LTCCs. LTCCs are made up of ceramic tapes and conductive metal paste, typically copper, silver, or gold. In LTCCs, the metallization layers are printed onto the unfired ceramic tapes. Because of this, there is a low loss of substrate, has quite a satisfactory thermal conductivity, and a high degree of passive integration. However, the entire fabrication process is very expensive. The figure below showcases a 60 gigahertz LTCC based patch antenna array and is the side view of the AiP stack up. The fabrication process for LTCCs start off with step 1, which is tape preparation. So it goes from raw materials to slurry to tape casting. In step 2, becomes the formation of metal traces and formation of vias, where the layers are blanking, and then they punch in the vias and they fill the vias. And then after that, the conductors are then printed onto the ceramic tape. And then after that is step 3, which is stacking. After step 3 is lamination, then co-firing, and then post-processing, which includes post-firing and electrical testing of the AiP. Moving on to the next conventional technology for AiP are high density interconnect, also known as HDI. HDIs use PCB technology and is made up of an epoxy glass substrate. This one is a fire retardant material, BT resin substrate, and a liquid crystal polymer substrate with copper wiring. HDIs have multi-level lamination of dielectric materials, as seen in the figure, and has a high density of wire routing. For the fabrication process of HDIs, typically focuses on 3 silicon via fabrication and copper filling. And as you can see on the left side of the figure, it starts off with silicon dioxide deposition, which creates a hard mask. And then after that is a photoresist coating and patterning. And then there's etching of the silicon dioxide and photoresist stripping. And then after that is the figure on the left ends with etching of the TSV and silicon dioxide removal. Moving on to the right side of the figures of part F, it starts with thinning of the wafer to expose the TSV. The next step is then silicon dioxide deposition on the backside. After that is a titanium copper sputter seed layer. And then there's bottom up plating until the TSV is filled. Once the TSV is filled, there's a copper overburden on top of a wafer that is removed by CMP, which is known as chemical mechanical planarization. The final conventional AiP technology I will be covering is the embedded wafer level ball array, which is also known as eWLB. This is a wafer level packaging where the wafer is placed on a carrier and then is encapsulated with a mold compound. As stated previously, there is no laminate substrate with this method. It is instead replaced with copper redistribution layers that have polymer or ceramic insulator layers with it. In this method, the redistribution layer acts as an antenna, as shown in the figure below. For the fabrication process of eWLBs, it starts off with TSV etching and passivation, as shown in the first block of the figure. After that, there's copper seeding layer deposition and plating, then removal and TSV passivation. The second block showcases redistribution layer deposition, patterning, and passivation. After that, the bonding side is then grinded down, and then the steps are then repeated for the TSV and RDL, again for the bonding side, so it's very similar to the first side. After the steps are repeated, there's a deep reactive ion etching, which creates a silicon cavity. Once the silicon cavity is created, there's a lead-tid solder bump deposition that occurs. Although antenna and package technology can have many advantages to traditional antennas, a lot of challenges arise with it as well. The substrate material in AiPs can often have dielectric loss, and the substrate itself can also often have warpage. This is typically due to poor thermal management, and this is because of a coefficient of thermal expansion mismatch between the substrate and components. This can cause delamination of the substrate and the IC. With poor thermal management, if it's not regulated properly, then the product may not safely operate at the temperature, which can cause a lot of defects. With the layer stack up and wiring design, they must be optimized, or else there can be electrical loss for the signal, and it won't run as smoothly as it possibly can. A lot of the for chip and BGA joints, a lot of times there could be an issue with the reliability of the packaging joints, and this could just be due to mechanical stress or environmental damage, which is what molding usually protects. With molding, however, if done incorrectly, there could be voids or bleeding on top of the chip, which could provide a weak point of the chip. And then finally, for wafer level packaging related challenges, has to do a lot with RDL processing. So with RDL processing, a lot of electrical defects can occur due to either metal layer breakage or warpage of the mold. And then all of these challenges can often work together to lower the overall performance of antennas. Here's the glossary, and here are my references.